Good morning, everyone. I'm glad we all made it safely in this morning. Welcome to Palynology Short Talk Session 8, Biodiversity, Ecological Interactions, Range Shifts, and Database Science. Once again, you have me, Jen O'Keefe, Yoshi Meizumi, Limi Mao, and Nicholas Strenberg joining you this morning as your hosts. We're looking ahead into the spring and ahead into next summer with I should say spring and summer in the Northern Hemisphere, fall and winter in the Southern, of course, with our session 9 for March, Polymorphs and Associated Environmental Indicators. We still have room for 2 more talks, so if you are interested in presenting there, please submit an abstract. Then we have session 10 in April, Vegetation Disturbances and Fire. All of you working on great studies of fossil charcoal, this is your home. We have room for 4 more speakers, please. Don't forget, session 10. Coming up in May, we have session 11, pollen production, dispersal, and taphonomy. This session is at the moment very under enrolled. Please, 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 those of you working on modern pollen studies, especially dispersal and taphonomy, submit an abstract to this session. With this session, if it is under enrolled, we will likely combine it with our postponed session 6, infographics and lightning talks. This session 6 is still hosted by AASP, the Palynological Society, and has a student award associated with it. They're very much looking forward to being able to grant this particular award. This will be the Von Bryant Student Poster Award and comes with a cash prize and 2 years membership in the society, which provides full access to the journal Palynology. So please, please, please consider session 11 for pollen production, dispersal, and taphonomy, and think about the infographic and lightning talk session. Then in June, we'll have our farewell session. It will have been a whole year of Palynology short talks and Palynology for the people. Can you believe it? This session will be a free-for-all open session, Palynology for all lovers of pollen. Any interesting paper is welcome. Then, just in case you're going to be missing Palynology, don't worry. AASP has decided that this year's session will be virtual, and their annual meeting, the week of the 9th through 13th of August, 2021, will be held online. Registration will be for a very small nominal fee, largely to offset the hosting platform software. And we're looking for papers on any aspect of Palynology. Sessions can be proposed by members or non-members. We welcome non-member participants and hope you'll consider joining the society. If you're interested in organizing a theme session, contact Steve Stuckens at the Natural History Museum in London. They're building the sessions to consist of keynotes, lightning talks, standard presentations, and posters that will be relatively short. I should say the sessions will be relatively short and will fit into convenient times for most time zones, much in the same way we've built PST. There'll be the usual AASP student awards at this meeting. That means this year you have the opportunity to double dip on the Von Bryant Prize. You could present a poster with us, with PST, and with AASP's meeting, okay? It's kind of an exciting development this year. And there'll be the wraparound icebreakers, social events, and so on, most especially the early career meetup meeting. So if you are starting to wonder, what are you gonna do without PST? Fear not, AASP is gonna pick up the banner, as is BES. Beginning in March and going through May, their Ecology Live session begins. If you haven't noticed the Ecology Live sessions on the BES website, BES Paleo suggests taking a close look and registering now for their free online talks for top ecologists and paleoecologists to be held every Thursday. So take a look at these. The lineup looks absolutely fascinating, and word is there's more in the works for later in the fall. Then, without further ado, we're going to turn our attention to our first speaker of the morning. Matteo, if you could load your presentation, please.
I share with you the screen.
Yes, please.
Okay, there you go. Can you all see it? It's okay? Okay, great. So, hello everybody. My name is Matteo Shumbata, and together with my supervisors Karina and James, in collaboration with Giovanni, we recently published a paper called Linking Modern Day Relics to a Miocene mangrove community of Western Amazonia. So a little bit of background just for getting you familiar with the concepts behind the study. So we focus on Miocene marine incursions into Western Amazonia. And at that time, a huge lake was present in the region, the Lake Pebas, which was influenced by marine incursions during warmer climate episodes, such in the mid-Miocene. And we find evidence of this in the fauna that today inhabit the Amazonia. But also we find mangrove pollen, suspected fossil mangrove, in the sediments from this area. And one open question is still there. Are there any relict plant species inhabiting nowadays Amazonian flora? So, more detail, the geological settings. So the Northern South America went through dramatic geological changes during the Miocene, which brought to the formation of the Pebas mega wetland system, which was periodically affected by marine influence, marine ingressions, when warmer climates made the sea level to rise. And we find evidence of this in the fauna that nowadays we find in the Amazon systems, in the freshwater rivers of the Amazon. For example, we find fish and dolphins that resembles marine counterparts, but they live in freshwater conditions. And also, as mentioned, we find a fossil mangrove, a suspected fossil mangrove, called Zonocosetes ramone in the sediments in the pollen records from this area. Furthermore, Bernal et al. Proposed a list of modern species which they suspect being modern relics of past marine incursions. And here are the Bernal et al. List, and we have noticed that some of the species that appear in the list were already assigned by previous research to fossil species, such as Cricotriporites dianensis, Psilamonocolpites rinconi, Psilabrevittricolporites devriesi, but also Acrostichium danefolium with Deltodiospora. So based on this, we asked some questions. And we wanted to know if Zonocosetes ramone was indeed a fossil mangrove. And also, we wanted to know which other species were part of this mangrove ecosystem in Western Amazonia during the Miocene marine incursions. And we wanted to identify species that were relatives of these fossil species in modern Amazonian flora. But ultimately, our question was, could Miocene marine incursions have promoted Amazonian plant biodiversity? So our study area was based in Amazonian Colombia, and we focused on 4 pollen records, which represented similar lithology and sedimentary environments. Though the Agua Negra didn't present any marine influence, And instead, Marigname, Apaporis, and Piraparana, presented in the pollen records, marine palynomorphs, or the suspected fossil mangrove. And also, I have to add that Marigname, Apaporis, and Piraparana presented similar species composition. So all of this together makes these pollen records comparable with each other. And we further focused on the Apaporis region, namely on the Apaporis and Piraparana pollen records, because they presented quite an high percentage of the mangrove, the suspected mangrove, Zonococytes ramone, up to 130 grains per slide as average. And then we applied our statistical techniques to the pollen records. And we wanted to find which species in the pollen record associated with Zonococytes ramone and the marine palynomorphs. And we used for this aim several clustering methods, which were tested out by a Kendall's W coefficient of concordance and fuzzy k-means clustering. So we obtained a list of species associating with mangrove, and we compare it with the Agua Negra section in order to exclude species in common with this pollen record. And once we did this, we compared our list of selected species with Bernal et al. List of modern species relics of the Miocene marine incursions, looking for overlaps with this list. So we used several palynological techniques, and via single grain methodology, we were able to isolate single grains from the debris and have them ready onto aluminum stubs. And then we analyze them via scanning electron microscopy, but also we use light microscopy to take images of our pollen species. And here an example of our groupings for the Apaporis section. Here you can see, Here you can see the coastal group with obviously Zonococytes ramone and the marine palynomorphs over here. But also we find Psylla brevitricolporites devriesi and Psylla monocolpites rinconi. Furthermore, we find two other groups whose species are suspected by other researchers being typical of vegetation of the back mangrove belt in Miocene coastal environments. So this instead for the Piraparana, again, Zonococytes ramone over here, and the marine palynomorphs, and still Psylla brevitricolporites devriesi, but also appears Cricotriporites guianensis. And again, the two back mangrove groupings. So here our SEM images of our fossil species, some of our fossil species. And based on this, we made detailed descriptions of the pollen types, and we compare them with descriptions of modern taxa, trying to find the nearest living relative in modern Amazonian flora. And we found out that actually Zonococytes ramone is a fossil mangrove, is Rhizophora mangle, as you can see here in comparison. And also we found that Psylla brevitricolporites devriesi is a fossil type of Humiria balsamifera, and tentatively assigned Forsteronia and UTEP to Cricotriporites guianensis and Psylla monocolpites rinconi. And here our light microscopy imagery. Here at the top, the fossil Psylla brevitricolporites devriesi, and here its modern counterpart, Humiria balsamifera, the fossil mangrove, and the modern mangrove, but also Psylla monocolpites rinconi and Cricotriporites guianensis. So here our fossil species list and Bernal et al. List. So we found a partial match. We found that the species that appeared in Bernal et al. List as being fossil species of modern species, Trigotriporites, Rinconi, and Devriesi, do also appear in our species list and associated with Zonocosetes ramone. But we found that the nearest living relatives don't correspond with the species proposed by Bernal et al. Indeed, we found Fosteronia possibly, and Euterpe possibly, and Eumeria balsamifera as nearest living relatives of these fossil species. But so this is a partial match because the family matches, but the genus, we couldn't get to a match with the genus. Then we look for analogs of our Miocene coastal environments, and we look for it in the Holocene pollen records. And we found that there's some overlaps between our species groups and the Holocene groups, especially for the back mangrove groupings. And we also found that during the Holocene, the mangrove ecosystem moved back and forth based on sea level changes. And we imagine something similar also for our mangrove from the Miocene. Also, the mangrove ecosystem is defined by quite a strict gradient in salinity and by soil conditions as well. So we suspect that the conditions that made the mangrove ecosystem possible in the Miocene lasted for quite a long time to the mangrove to thrive and be established in these environments. So to sum up, Zonocosetes ramone is a fossil mangrove, and we found 35 taxa associating with this taxon. And of these 35, 14 were closely associated with it. And we found the nearest living relatives of some of the fossil species associated with this mangrove, and they partially matched with the Bernal et al. List at the family level, at least. But also the nearest living relatives do also occur in coastal and terrestrial environments, which was a requirement for Bernal et al. List for its species. And we propose that our selected taxa may have arrived in Western Amazonia via the marine incursions and then adapted to the freshwater conditions. So in conclusion, we propose that marine incursions may have been drivers of the adaptation and evolution of coastal species to terrestrial environments in Western Amazonia. And also, we could not completely match our fossil species with Bernal et al. We focus on sediments of Amazonian origin, and we believe that the sediments, for example, of Andean origin may bring similar signals of marine influence, and then we could find more species matching with Bernal et al. List. And in the end, we want to propose a new procedure combining statistical and palynological techniques that find species associating together in the pollen records and assign them to modern flora. And well, I would like to thank you all for your attention and remind you that this publication was a contribution for special issues to Volker Mosbruch career. And any question?
Thank you for that talk, Matteo. We've got 5 minutes now. If anyone has any questions, you're very welcome to turn your microphone on or to type in the chat. Okay, we've got our first question in the chat here. Great talk. Did you find any relationship between the origin event and the marine incursions?
Well, we haven't looked into it, and the only link that we found is that species that nowadays present coastal and terrestrial habitats, some of these species were associated with this mangrove Zonococytus ramona. That's the only link, but we haven't looked into origination of these species.
Great. We've got another question here. You showed fairly significant differences in size between modern and fossil pollen. Is this an acetylosis effect or something else?
Well, I may not be knowledge enough on this. I don't know if that can be linked to acetylosis effect, but I guess that well, there's 50 million years dividing the two fossil pollens, the two pollens, and I'm not very familiar with this, but I guess that through time the size may change, but other fundamental characteristic of the fossil pollen were identical, except for the size. Maybe it can be also that the fossil pollen that we found, since we analyzed around 10 of them, were just a smaller population, let's say. That can be.
Great, thank you. Another question. Modern Rhizophora has only one species in America. According to your fossil pollen types, did you find any variety or ornamentations?
And a variety of ornamentations. I think we also looked in other Rhizophora into the genus. I think, if I'm not wrong, into Rhizophora mucronata. But we didn't look into varieties of ornamentation, if I'm not wrong. And yes, we could assign quite definitely the Rhizophora mango to our fossil species.
Brilliant, thank you. Okay, we'll just see if we get any more questions, but if not, we can introduce the next speaker. Okay, if
one more question, Camille.
Great. The next question, is there an opportunity to do similar analyses comparing other plant traits? How robust is it to assume that pollen morphostructure alone can represent many of the functional traits?
Well, I guess that the same analysis, yes, may be done also on other plant traits. Well, actually, this analysis is based on the appearance of the species in the pollen record, not exactly on the morphology of the pollen. The morphology of the pollen comes later when we look for modern relatives. So actually, the analysis I don't think is applicable to other plant traits. It's applicable to data of abundances. Yes.
Thank you, Matteo.
No problem.
Okay, so our next speaker is Yufeng Li, and the title of the talk is Orographic Evolution of Northern Tibet Shaped Vegetation and Plant Diversity in Eastern Asia. Great.
Okay, can you see it?
Yes.
Okay, thank you. Hello, I'm Su Fengli from Xishuangbanla Tropic Botanic Garden, Chinese Academy of Sciences. Today I will introduce recently published work. It's combining modeling results and fossil data. So it's a little bit different with palynology, but we do collected many of the palynological data and also some maker photo data. So first, I want to introduce you with this topography of Asia. So the most important feature we can see is the Tibet. So the Tibet uplift in the Sinozoic is a very big topographic change, which affect the Asian climate system. Nowadays, Asian climate system, we can say it's include the East Asia summer monsoon and the South Asia summer monsoon and the Asia winter monsoon and also the westerners. This is a major climate system which affects modern vegetation and biodiversity in Asia. And the Tibet, actually, we can see it's including the different terrain and the different regions. From the south, it's Himalaya, Lhasa terrain, and Changtang terrain. And the north is the Songpan-Gansu terrain, and also some other ranges like Caidam Basin and the Qilian Mountains. So this is a background of the Asian terrain and the climate. I will, sorry. So I will focus this region, the southeast of China. This region in the modern days is dominated by the evergreen broadleaf forest, and also with very higher biodiversity. Because it's lots of rainfall and also very good climate condition. So we call this area is the land of fish and rice because there is a lot of fishes in these regions, and also the people planted rice in this area. But how this climate and the vegetation and the biodiversity established, we can first find some literature. They have doing some analysis on this. For example, the Sun and Wang, they have published a paper based on lots of fossil Pliocene to Pliocene. The vegetation changed dramatically, especially from the Oligocene to Miocene. So from Paleocene, Eocene to Oligocene, there is a dry belt in the center of China. But from Miocene, we can see the southeast of China, it's become very wet and humid. And the Pliocene also similar with Miocene. So there's a big change from the Paleogene to the Neogene. And later on, there is another paper published by Guo Zhentang. They also combined many pollen and megaFossil, and also other geological records. They show that the arid or semi-arid belt do exist from the Paleocene to the late Oligocene, but it's changed from the Miocene to Pliocene. So these two papers show there is a big change from the Paleogene to Neogene in China. And very interesting, there is a paper published 3 years ago. They use many of molecular data, and they find that many of general of modern plant from east of China, they established about the early Miocene. And another paper, they also use molecular data. They show that the rhododendron flora from southwest of China and also metal sequoia flora from southeast of China. Both of these floras are established from the early Miocene. So this fossil and the molecular data also show that similar changed pattern. The biodiversity changed from the Paleogene to the Neogene, and the vegetation changed dramatically from the Paleogene to Neogene. So our question is this. So the first is, what way did successive Tibetan or orogenic events affect climate? The second is why the vegetation and biodiversity change in East Asia so dramatically from the late Paleogene to the early Neogene. So to answer this question, first we collected the pollen and the megaFossil data from the previous published literatures and also recent published papers. And we collected about 205 fossil sites. And there is more than 300 records. And we also classify the fossil data to arid, semi-arid, humid, or semi-humid. These 4 types. And we found that there is really a big change from the Paleogene to Neogene. So actually, it's from the Oligocene to Miocene. We can see the arid or semi-arid belt changed to the to another pattern. The southeast China is very humid, and the vegetation is humid or semi-humid flora, and the northwest of China is become to arid or semi-arid floras. But this flora is not easy to compare with the modern results. There is a vegetation model, we call this SDGVM. This is quite popular in vegetation models. And to compare with models, we classify these fossils to SDGVM criteria. And we so classify this fossil to 6 different types. The first is barren, and then grass. Because we have no C4 or C3 information, we cannot assign this grass to C3 or C4. And then there is a deciduous broadleaf, deciduous needleleaf, and evergreen needleleaf, and evergreen broadleaf. So we have the fossil data, and then we can do some modern results. There is a quite popular so this right plot is actually the Tibet topography plot. So we can remove the Tibet topography, and this is the flat Tibet, and we can compare these 2 different experiments. And we can set more detailed experiments. For example, we can set from the south to the north uplift of Tibet, and we can analyze the results from these different experiments. But it's still not enough. there is maybe many of different topographic conditions. So we set up the debate to about to 18 different conditions. So the first one is based on the native Olexin, the chanting stage topography. And then we can delete the Tibet. So this is a flat Tibet. That means the Tibet is 0. And then this is 1,000 meter Tibet. The Tibet is no higher than 1,000 meters. And then 2,000 meters, 3,000 meters, 4,000 meters. And then have different effects on climate. So we also set the Tibet to different uplift conditions for different regions. For example, the first one, this is the Ganges Mountains uplifted. The Ganges Mountains we set up is to 4,000 meters. And then the South Tibet, this is the Lhasa terrain. We set up this to also to 4,000 meters. And then this is the Changtang terrain. We can also set to 4,000 meters. And this is the northeast Tibet. We call this Songpan-Ganzi terrain. So we can also set this to 4,000 meters. So we set up different uplift of different terrains to find if there is a difference. And when we use this climate model, HARD AM3, this model is based on the University of Bristol. And we can use this model to product different climate parameters. But the main result is temperature and precipitation. And if we have this climate results, we can put them to SDGVM and JEDA DGVM. So here is the example of SDGVM. We can see the, we call this the shelf-fed dynamic global vegetation model. This vegetation model can product 7 different class of vegetations. There is a C4 and a C3, but we know that because in the fossil data, we normally have low this results. So we combine the C4 and C3 together. And also there is another vegetation model. We call this JEDA DGVM. From this, so from the blue color to the red color, it shows biodiversity increased. We call this biodiversity functional richness. That means there is how many of functional types of the model, the disseminated vegetation types that can represent the richness of plants. So here is the results. So we have 18 different experiments. So we have 18 different results, 80 different vegetation results. I cannot go into the details, but I can show you how we compare the modeling results with the fossil data. So we focus on the southeast of China, and here we can see we can compare with the modeling results with the fossil data. If they have very similar results, they will keep it. So we can we can select this vegetation results, which are quite similar with the fossil data. From the first panel, we can see there is a very few. There is some broadleaf. So the green color means green color grids represent the evergreen broadleaf forest. So we can see in the southeast China, there is a very few of these evergreen broadleaf forest. This is similar with the Palynology conditions. And when the Changtang, so the middle panel and the lower panel plots represent the higher mountain of north and northeast of Tibet. We can see that there is a lots of evergreen broadleaf forest, which quite similar with Neogene fossil data. So we select these simulations to compare with the fossil results. And then we put this topography conditions and vegetation and the biodiversity together, which can clearly show the change pattern. So if the Tibet from 1 to 3 and to update from the lower Tibet to higher Tibet, and generally generally it shows from the South Tibet update to the North Tibet, and we can see in the southeast of China, the evergreen broadleaf forest increased accordingly when the Tibet uplift. But even the Gandhisi Mountains is high, the evergreen broadleaf forest is still not too much, and the biodiversity is still lower, still quite low. When the Lhasa terrain uplift, so the first panel of this plots represents the Lhasa terrain uplift. The evergreen broadleaf forest in southeast China is still not enough to compare with the fossil data. But when the Changtang, so the North Tibet and the northeast of Tibet, the Changtang terrain and the Songpan-Ganzi terrain uplift, in the southeast of Asia, there is lots of evergreen broadleaf forest, and the biodiversity changed a lot. So that means this from 5 to 6, this represents the Neogene conditions. So why the vegetation and the biodiversity changed like this? We compare the temperature and the precipitation and the other climate factors with the vegetation patterns. And we found that the most significant change is precipitation. So here, the left panel from A1 to A3, this is the winter precipitation. The middle panel is the summer precipitation, and the right panel, C1 to C3, this is the monsoon seasonality index. This index is quite a simple one. We just use the summer precipitation minus winter precipitation. That means the difference between summer and winter precipitation. So we can see from when the Tibet uplift from Tibet, the winter precipitation and the summer precipitation increased, but the seasonality decreased. That means the winter precipitation increased a lot. It increased more than the summer precipitation. And also, the similar pattern we found from the South Tibet uplift to the North Tibet uplift. The winter precipitation increased significantly than the summer precipitation. So that means the winter precipitation is the most important factor control the vegetation changes. And we also analyze the tropospheric winds and 850 hPa. And so here the A and C is the winter winds, B and D is the summer winds. We can find that the A and B is the lower Tibet conditions, C and D is the higher Tibet conditions. So we can find the most significant change is the winter precipitation change in the southeast of China. When the Tibet uplift, there is a significant change from the southeast of ocean. The winds, so this means the winds can bring some waters, some moistures from the oceans. The summer winds also increased a little, but not so significant. And there is another plot which shows a vertical velocity. This is represents the moisture goes up or goes down. So in in this plot, the green or yellow color means the moisture goes down, and the blue color means the moisture goes up. So we can see the significance is the moisture goes up in the winter when the goes up in the about 30 north degree, but it's not so significant. So we can use this figure to summary our results. So when the Tibet is uplift from south to north, so the Paleogene, we generally think the Gandesan Mountains and the Lhasa terrains are high, but this topography is not higher enough to block the winter monsoon. So in the winter monsoon is still very strong, and the winter climate is very dry. So there is in the southeast channel, the vegetation is dominated by the evergreen broadleaf forest, and the diversity is quite low. But when the North Tibet uplifted in the Liujin, the winter monsoon is blocked by the North Tibet mountains. So the winter monsoon is not so strong, and there is a moisture from the southeast ocean that can bring moisture to the southeast channel. So the vegetation changed to the evergreen broadleaf forest, and the biodiversity increased. So this is our map. This is a plot we can clearly show how the climate change and so summary for our results. First is the Tibet update can profound effects on vegetation and plant diversity change from the Paleogene to Liujin by changing monsoon patterns, especially intensify both summer and winter precipitations. And the second one is winter precipitation may play an important factor which affects vegetation and biodiversity in East Asia. The northeast part of Tibet is much more important than other part of Tibet in controlling the climate and vegetation. So this is supporting the theory that Tibet may uplift and grows northeast world. We want to use one sentence to summary our results. So we can use this sentence: without the growth of northern Tibet, there would be no land of fish and rice in Eastern Asia. So this is my talk. Our work just published last month. If you have interested in this work, you can read this paper. And our work, this work is supported by the National Science Foundation of China and NERC in UK. And I want to thank many of the colleagues from China and UK. Thank you.
Thank you so much, Yufeng, for that talk. And I thought it was very nicely summed up at the end with that sentence there. We have a couple of minutes for questions now before our final speaker. So if you want to unmute yourself, or if you want to type in the chat with any questions for Yufeng. Okay, if there are any questions right now, maybe some will come up at the end. Yeah, if you can stop sharing your screen, Shufeng, that would be brilliant. Thank you so much for your talk. Brilliant. Okay, so I can introduce our third speaker now. I hope that the snow hasn't been too disruptive, but the talk is reconstructing the Cenozoic history of fossil pollen and Stratopolis catabombus using convolutional neural networks. And the speaker is Ingrid Romero.
Okay, let me share my screen. Everybody can see the screen? Okay, yeah. Hi everyone. So yes, as Nicola says, I will be presenting reconstructing the Cenozoic history of the fossil pollen of Stratopolis catatumbus using convolutional neural networks. So we have, and we know that pollen is an excellent proxy to understand the evolution of lineages of plants. However, many polynomorphs that are older than 2 million years have no clear biological affinity, especially in the tropics where this record is very diverse. And one of the reasons is the low resolution of the pollen morphology. Is that how in the figure, we see that with less morphological characters, the identification is less accurate. So this limits the ecological and evolutionary interpretations that we can get from this record. And that's how it is necessary to increase the morphological resolution of fossil pollen grains to improve not only the taxonomic identification, but also the ecological and evolutionary inferences. So in this study that was published like a few months ago in PNAS, oh, wait. Oops, am I like upside down? Oh, chamfle. Let me see if I can fix that.
No, it's okay, Ingrid. It's
okay. Oh, got it. Sorry. So in this paper, we assess how the taxonomic identification in the fossil pollen can be improved by combining air scan images with machine learning methods by using these fossil morphospecies. So, okay, let me see. Okay, so first we have that air scan, that is a confocal super resolution microscope, can capture the external and internal structure of modern and fossil pollen. This can also capture with enough detailed internal ornamentation, although is with lower resolution than electron microscopy, we still can see or identify potential diagnostic characters. And the optical microscope can also capture the three-dimensional morphological data, which is important for quantitative analysis of morphology. In the other side, deep machine learning methods, such as convolutional neural networks, can improve the efficiency and accuracy of fossil pollen identifications because these can efficiently process an image and analyze visual data by extracting features that encode morphological characteristics such as shape and texture. That is what we use for biological classification. So here in this figure, we can see that the input for the CNN models is an image, and by selecting a section of the image, the machine learning model does a hierarchical classification, and at the end give us as an output potential candidates of what the image is and the probabilities or confidence scores. So for this study, we select Stratopolis catatumbus because it has a distinctive morphology. It has been found in the fossil record since the early Cenozoic, about 60 to 65 million years ago. And here in the animation, we can see how has been the paleogeographic distribution through time. Also, it has a pantropical distribution, and it has been associated to lowland environments. In South America, has been associated to wet environments, and in Africa, more to drier environments. Interestingly, some of the mother candidates of the genera are part of the legume tribe that is Amherstia, subfamily Deuterioideae, and in the phylogeny and ecology of the modern group, it has been proposed that it has a warm and wet origin, similar to coincide with the ecological interpretation that we had initially from Catatumbus in South America. And at least 28 genera of this tribe have a similar morphology than Stratopolis catatumbus. So here we selected 16 genera of those 28 genera. And here we can see the genera and the number of species that we were able to analyze. This variability in species was limited by the availability of herbarium material, and in total we imaged 459 pollen grains. And this dataset of images was then divided in two groups. One group in which 70% of the images were used for training the models and 30% of the images were used for testing. It is important to highlight that the specimens in these two groups were randomly selected, and there with the collaborators we developed 3 convolutional neural network models that have a ResNet architecture. So the models that we used were maximum projection model, multi-slide, and fuse model. Following, I'm going to explain the models and the results that we obtained first using the modern pollen and training the models. So the first model is the maximum projection model and use as an input a maximum projection image of the specimen. This means that the model only used the external structure of the wall. The performance of this model was the lowest, with 83% of accuracy, in which only 3 of the 16 genera were identified as themselves 100% of the time. Cynometra, however, was the only genus that was never identified as itself. It was always identified as Macrolobium. The second model is the multi-slide model, and this one used as input a subset of images and mainly works with the internal structure of the wall. The performance of this model was higher than model 1 with 89% of accuracy, and in this model, Cynometra also was never identified as itself. The last model is the fuse model, and this uses as inputs the maximum projection of model 1 and the subset of images from model 2. So it used features of the external and internal structure of the wall. This model had the higher performance with 90% of accuracy, in which 10 of the 16 genera were identified as themselves 100% of the time. However, Cynometra also was always identified as Macrolobium. So we review what was happening with Cynometra, and we compared the images of Cynometra and Macrolobium, and we had 2 potential explanations of this problematic identification. First is the sample size, because Cynometra was the genus with the smaller number of images in which only 1 specimen was imaged. And the second is that probably the herbarium specimen that we use the identification needs to be reviewed. So for further studies, it is important to have a bigger sample size if it's possible. Now, for the fossil record, we select and image 48 fossil specimens from Africa and South America. The fossils from South America were from the Miocene and Eocene, and the fossils from Africa were from the Eocene and the Paleocene. And here we can see an example of 3 of the fossil of Catatumbus image, and we can see variations in the preservation variations in the external structure and variations in the internal structure of the wall. So we basically, to classify these fossils, we use the 3 trained models, and these were the results. So first, we have a predicted model or label, sorry, that is the genus with higher affinity. And for each predicted label, we have a classification score that goes from 0 to 1. Here in the table, we have that the fossils are highlighted in, the fossils from Africa are highlighted in blue, and the fossils from South America are highlighted in green. But in the identifications in blue are from African modern genera, in white for pantropical modern genera, and in green for neotropical modern genera. So what we found, first, that most of the specimens, the identification have consistency among all the models or between 2 of the 3 models, and only six specimens had no consistent identifications, and they are highlighted in red. We also found that the African specimens were identified mainly as pantropical and African genera, and the South American specimens were mainly pantropical, South American, and some were African. So these results have important implications in biogeography and phylogeny that I will explain later. In addition, we compared these identifications of the convolutional neural network models with traditional morphometric analysis, in which we basically collect quantitative and qualitative variables from all the fossils and 60 extant pollen grains. And we use a non-multidimensional analysis to analyze this data. So what we found as a general result, we had that most of the South American fossils were identified as neotropical modern genera, some as pantropical, and some as African. And the African fossils were mainly identified as pantropical or African genera, which is consistent with the CNN analysis. We also reviewed the identifications that were proposed for the fuse model, that was the one with higher performance, with the non-multidimensional analysis. And we had that at least one of the identifications or genera proposed in the fuse model was also one of the candidates proposed in the NMDS model. And some fossils that had no consistent identifications, neither in the convolutional neural network models or in the NMDS, are probably suggesting extinct morphologies. That is important too, to keep in mind. So overall, our results show that the CNN models were more consistent than the NMDS, because they give us 1 or 2 candidates. Meanwhile, the NMDS can give us up to 5 potential candidates. So finally, we place the fossil specimens in the phylogeny that has been proposed for the Amherstia group. And here in color, we have the biogeographic distribution of the modern genera. So blue African, white pantropical, green neotropical. The shape are the fossils, so the round ones are from Africa and the square ones are from South America. And what we are seeing, that South American and African fossils were identified as African and pantropical genera. And these genera diverged from the tribe early in the Cenozoic, around the early Eocene. But interestingly, we have that only South American genera fossils, and from the Miocene were the only ones that were identified as South American modern genera. And when we look the phylogeny, the neotropical genera diverged from the, although Stratopolis catatumbus in the fossil record has been found since about 56 million years ago, the neotropical genera diverged later, like in the Oligocene and Miocene. So these identifications are consistent not only with the biogeography of the fossil and the modern group, but also with the phylogeny that has been proposed. So we have that this result has a consistency, are consistent with these other information and with the evolutionary history of this group. So in conclusion, we have that the convolutional neural network models efficiently discriminate several morphological differences in pollen. Most of the identifications were consistent with between the fused model, the non-multidimensional analysis, and the visual assessment. So, but the convolutional neural network identifications were more definitive than the more quantitative, the other analysis. The fossil classifications, as I say, show biogeographic and phylogenetic consistency with the extant group. And we also have that the fossils that had not consistency are probably suggesting extinct morphologies, which is important when we are talking about the evolutionary history of plants, and that this is extinct potential groups. We don't see that in other analysis, only when we are looking the fossil record. So we also had that the fossil pollen is probably more diverse than what we previously estimated. And with this model, we have the potential to improve these identifications, and this will open new avenues for the study of the evolution and ecology of plant clades with new interpretation using pollen data. So with this, I want to acknowledge that this project was funded by the National Science Foundation, the University of Illinois, and the Palynological Society. Thank you.
Thank you so much, Ingrid, for that talk. That's brilliant. Yep, so if you've got any questions, just put them in the chat there or unmute yourself. We already had one question for you, Ingrid. So how did you randomize the selection of your specimens?
So basically what the model does is you put the images in the system, and you use program to divide the data set into groups. So you don't know which image is going to where, but what you know is that the images that were used for training are not the same that are using for the testing. So basically the images that are in the testing group are images that the model has not seen when it was trained. So that's how we tested the performance.
Brilliant, thank you. Yep, another question here. Great talk, Ingrid, thanks. Is the CNN mainly extracting information on shape and texture, or will the pollen size be incorporated too?
That's a very good question, and I don't know, because we were trying to see, there is something that the computer scientists, the collaborators in the study did, and is try to highlight maybe which parts of the morphology the models are maybe selecting. And when they did that, it was highlighting all the grain. And meanwhile, when they do that with, for example, images of birds or plants, they have that it selects some specific regions. You know, for example, in birds that we have this coloration pattern, but with pollen, it selects everything. So we are not completely sure what is selecting, but it's interesting that the model that has a morphological data from the external wall and the internal structure had the best performance. And me as a palynologist, I was thinking, when we as a palynologist are looking pollen, we're looking those two type of morphology, right? To have a stronger identification. So I think that's what I found pretty interesting.
Fantastic, thank you. Another question from Shufeng. Can this method be applied to various types of pollen?
I will think so, yeah. And the cool thing is we as a palynologist have been doing a really good job already making a first classification of fossil and potential affinities. So having that information, we can start experimenting, for example, with Mateo's presentation and with Rhizophora. What if we can analyze several of these fossils and compare with the Rhizophoracea family? Probably that's gonna give us more information about the evolution of this group and how maybe diverse in South America. So yeah, I will think so.
Brilliant. And another question here from Thomas. Nice talk. Could you give a bit more detail on the software and the methods you used? Is it like code-based, or what specific language and what packages and software did you use?
Well, that's a good question. I have not much information about that, I have to say, because I was not the computer science developing the models. But I will say they were, when they make the models, it was on MATLAB. And I know the code was included in the publication. So what I can do is send the link where the package that was developed is in to use, and maybe I can put you in contact with Shu, that was the collaborator that created the models.
Thank you, that's brilliant. Great. So if there aren't any more questions, I think we can close with some remarks about future sessions, perhaps.
All right, some advertisement from our sponsors because they've been brilliant so far this series of sessions. BES Paleoecology Group says, hey, all of you, we're doing great paleoecology and presenting lots of great paleoecology, so please remember to join our organization. Dues for the SIG, the Paleoecology Group itself, are free, although joining BES is highly recommended and donations are always welcome. BES dues are very reasonable, and hey students, there's a 12-month free membership available. Don't forget that part. First 12 months on the society. That's a great benefit, along with their newsletters, blogs, tweets, email listing, and special events. Take a look at @BES _ paleo on Twitter for links to weekly paleoecology blog posts and details on the upcoming R workshop. And the Palynological Society says, hey, we love you guys too. Come join our organization. We're the Specialist Society. We support palynology across the geologic timescale, from modern aerobiological studies and pollengenesis studies all the way to Precambrian tiny microfossils teasing out the origins of life. Dues here are also very reasonable and go almost entirely to support student research in palynology, either through the student research grants or student travel awards to annual meetings, as well as awards for students within the meetings themselves. Be sure to follow AASP TPS on Twitter and Facebook for updates and announcements, including further information about their upcoming annual meeting when we wrap up with the Paleo Short Talks. Our next session will be on March 16th. There are 2 spaces still available, so please, if you have a talk, do sign up to fill those last 2 spaces. Session 9 is Polynomorphs and Associated Environmental Indicators. So this could be anything from my fungi to the newest pollen study out there. And with that, we will see you all in in March. Thank you all very much for attending today.